just move directly to our next speaker, Giles Bergel, who is a digital humanist based in the Visual Geometry Group in the Department of Engineering Science at the University of Oxford. Giles is a book historian by training. He manages a research and engagement program on visual AI for cultural heritage and humanities research. Over to you, Giles.
Thanks, Laura. I hope people can see my slides. No one says they can't, so I'll carry on. That's very good. As Laura said, I'm a member of the Visual Geometry Group, which, like John's group, are a large, long-established computer vision research group. Some people here may have heard of the VGG family of neural networks, which came out some time ago, but is still widely used in visual AI pipelines. We're based in engineering departments at Oxford. I'm not an engineer myself or a computer scientist. My background is in digital humanities and book history. And my perspective, therefore, is perhaps more applied than John's perspective, although I think there's a great deal of overlap between his talk and what I'm going to say today. Broadly, I want to talk about what people can expect to be able to do with computer vision and cultural heritage, based on some examples of collaborations we've been involved in. I also want to talk about what is desirable but hard, maybe too hard, with current methods, and also want to talk about what computer vision can do for computer vision. Okay. So this is the kind of activities that VGG does through its collaborations in cultural heritage. We offer training and support. We carry out collaborations directly with researchers and institutions in cultural heritage. We do focused implementations and demos using research questions and materials in that sector. We're involved in co-creating data sets and making them available for reuse. And we provide open source software. And here are some examples of those pieces of software. One of our major outputs at present, which we release in a more user-friendly form than most academic software. It's all open source and free, and some of it runs on standard desktop environments, others it requires virtualization environments like Docker. We aim, with our current grant in particular, to get this software as close to users as possible and as many users as possible. To a large extent, what we offer mirrors the tools that are available from commercial cloud-based technology companies with whom we work. We're familiar with Google and Facebook and Amazon, but our tools are non-proprietary and open source, and therefore freely available to download and install in your own systems, and for you to run over your own data sets without handing them over to a technology company, or indeed to us if you don't want to. We place a lot of importance on creating well-curated data sets, which we also release for general use for training and testing new methods. And I think it's particularly important for cultural heritage collections to be able to use data sets that are relevant for their domain, they're adapted for their domains rather than just generic image sets. And that can be interrogated perhaps for bias, something that everyone involved in AI or an interest in how it's used is rightly concerned about at the moment. Also, I think that perhaps cultural heritage collections aren't always aware as they might be that their data is of interest for AI companies and researchers such as ourselves. It has value, that the data that cultural heritage memory organizations assemble is well curated with good provenance, is well characterized for training purposes, and this is worth something, in particular in aggregate. And if you're involved in the collaborations with someone like ourselves or a technology company, I'd urge you to recognize that you have something of value and to negotiate accordingly. And I find our heritage organizations are increasingly aware of this. I mean, this relates to my first point on why are we doing this, why are we involved in collaborations with cultural heritage, because cultural heritage organizations generate large and diverse image data sets. You have things that computers have never seen before, such as some of the wonderful artworks that John was showing before, and it has good metadata. And John's point about the kind of problem with metadata, I think, is well taken, that metadata may be inaccurate. You know, there are other ways of searching collections than, or training AI systems and using metadata, but if you're going to use it, it might as well be good quality. And museums, libraries, galleries tend to have better metadata than can be gathered, for example, just by scraping Flickr or the open internet. Also, humanities research questions that are difficult to address computationally and are intrinsically interesting. An academic research collaboration can be beneficial. It can demonstrate impacts defined broadly. This can be through creating discovering new research questions, doing something more efficiently than has been done before, finding out something about materials, about bias, about provenance of data. We define impact in various ways, and always in the ways that are specific to the domain that we're collaborating in. By working with current research organizations, we hope also, this is a particular interest of mine lately, is to improve the curation and sustainability of AI models. And this is kind of relevant to what John was saying in relation to his blockchain project, that nobody currently has a very good model for making AI models available, accreditable, sustainable, and interrogable. We all use GitHub, something like that, and there should be better ways of so doing. And who better to develop good protocols for these things than institutions that are already doing this with diverse forms of data. Importantly, collaborations also with cultural heritage and humanities researchers often raise questions around accuracy, bias, accreditation, or methodological assumptions. So it can be a kind of a critical relationship, a dialectical relationship, which raises the question of broadly, what is AI good for? So I want to talk about the last of these through an example of some specific projects we've done with partners in cultural heritage. Okay, so here you can see image matching and image classification, which are two basic computer vision tasks, two basic forms of image recognition, both of which we do. So image matching is, or so-called instance-based image retrieval, asks and attempts to answer the question, are these images of the same object? By example, not using metadata, just by a query. Whereas image classification asks, what kind of object is this? Okay. So I'm going to start by talking about image matching, which uses very similar technology, or we have used very similar technology to what John outlines, using so-called bag of visual word algorithms, in which these little red ellipsoids here, which are sift features, exactly what John mentioned, are used to retrieve two images of the same building from different angles and a different scale. We call these aggregated features, these aggregated sift features, visual words, which is an analogy we borrow from computational linguistics, with whom we share a lot of methods, things like topic modeling, various kinds of neural networks that have been, or AI techniques that have been performant with tasks like natural language processing, such as transformer networks. We take a lot of inspiration from work in that domain, as well as applying methods that are relevant to images. A bag of visual words contains geometric features defined by differences in texture, which are scale invariant. As you've seen, the size of the features we're attracting within the size of the object within which we're matching, it varies. That is also those features survive rotation and skewing, but not flipping or warping. So if this image was in a mirror, we couldn't retrieve that without doing some modification. Features have to be within the same plane, which details on the facade of a building like this very much are, regardless of the angle of view. So those can be efficiently retrieved using this method. And this technology we make available through this software, VGG image matching software, or excuse me, VGG image search engine, or VICE. It's free and open source and under active development. And it can do things like retrieve logos in video footage. So here's the Google logo and various instances of canned footage in a data set of 10 million keyframes from the BBC video. That demo is available, is online through this link. And you can see the Google logos retrieved from, it looks like exactly the same image at the top 3 rows, but it's actually the introductions to different news clips. It's just reused footage. later down, you can see the same logo being used in slightly different contexts. And that's the kind of thing that this visual word-based approach is extremely good at retrieving matches. Here's a recent development of the same technology running in a collections management capacity. So here the task is matching and deduplication of studio photographs. The Ashmolean Museum in Oxford, like many organisations, like myself, has an issue with duplicates. And prior to moving into a new DAM system, they gave us 262,000 images, of which we found there were 97,000 duplicates in pairs and a smaller number of larger sets. So this is a good example of a very kind of practical form of computer vision that based around reducing costs and management overheads, and we found it works extremely well for this purpose. Slightly more challengingly is matching features in images that have a low amount of texture within them. So these Assyrian clay tablets have a shallow relief and not much variation, unlike some edges of a building. We can match some features, but this is the kind of thing that we would like to be able to do more accurately and at larger scale than we currently can. Matching printed illustrations, we can do extremely well with this technology. So I'm just going to dwell on an example of this, this work. The task here is finding instances of impression in the same printing surface. And here's a bit of footage of our demo. We're retrieving matching woodcut illustrations from this collection here. As you go down, we find things that are pretty much the same, but right at the bottom, you may see that we have some examples of things that are very close copies, but not identical. So these illustrations have some small differences. If you look at the backgrounds of the grass and at the hat, that's not quite the same thing. But this is not quite what the classifier was looking for, but it's a kind of lucky match in some ways. What if we want to find things that are more dissimilar than that, but are clearly related? So here we've got a catalogue view of the same illustrations, which have been automatically extracted and clustered together. And you can see the corpus contains things that are very similar, but not quite the same thing. How can we aggregate these in a way that is meaningful to users while not including things that are less relevant? The problem of similarity in this context is that we need to identify a common feature space, whereas relevant illustrations may be only partially similar. Similarity may include partial copies or depictions of the same subject. Then a feature space that accounts for that kind of broad variation, which is common to similarity in general, may lose granularity when it's venturing outside of these kind of very specific matched features. Moving to image classification, we find some related problems, but coming from a different direction. So the task here is much more broadly based than image matching. We want to find every type of aeroplane, every image which contains the same kind of thing rather than exactly the same object. This is a collaboration that we do with Art UK, formerly Your Paintings, who provide us with images of 200,000 oil paintings, which we were tasked with finding objects in them or broad form of similarity. So we can find boats reasonably successfully. Perhaps slightly more interestingly or suggestively, we can search by colors. And we can search by geometric features, by textures. So this I find particularly kind of elusive and interesting, that we can, if you look at the visual relationships between ships, sails, abstract patterns and so forth. We can find dogs as well, but often featured alongside horses in this data set, which leads to an interesting example of bias in training data. So because in the corpus of British painting, particularly paintings in public ownership, which is what the Art UK data set is based upon, This is a data set of elite material. It contains hunting scenes, and this leads to some misclassification. So one of the results here for my query dog returns an image that contains no dogs at all, but does only horses. The explanation for this is that dogs and horses are visually somewhat similarity, but in this case, similarity is not in fact useful. The training data contains both dogs and horses, so the classifier doesn't learn features that are specific to dogs. So the problem of similarity in this case is that, again, image classification requires identifying a common feature space. But identifying images as similar is highly contextual. It can include the same objects with different backgrounds, and it's also necessarily subjective. Different people find different things similar according to their own experience and interests. One approach to this is to provide a more like this button. So in this example here, I've searched for guitar in Art UK with Google Images as input. So I've inputted the term guitar, which has retrieved some images of guitars entirely unsorted from Google Images. And the results are fairly good at kind of first pass. I mean, you do see some things that clearly aren't guitars. I have no idea where the boomerang came from. But what we can do is by clicking on the plus sign in this interface, provide similar results. This is a kind of more like this feature, and retrain using those examples. And what we get out is something a little bit better. We've got rid of the boomerang. We still have Charles I with the stick in the bottom row below. And again, this is something that's done entirely with visual queries. I mean, we can use a tag test of images as input data, or to organize some visual concepts, but the refinement of this is done entirely visually. And this can be scaled up, so it's not too hard to imagine how one could scale this up to the level of collections in order to discover similarities across collections, or in order to kind of, if you like, refine the search through the example of how images have been understood in other collections. Okay. Now, similarity is only one kind of relationality. There's also influence, which is a very specific kind of visual relationship, which may or may not present visually. In this case, it does. So this is a collaboration we're doing with Stephen Harris, who's a plant science librarian at Oxford.
Giles, can I just give you like a 2-minute endpoint, since we're going to run out of time? Thank you.
Thanks, Rob. So I will wrap up in exactly 2 minutes. So we can readily see here that these two images are similar to the point that one has to have been copied from the other. And if we want to trace those relationships, influence is a concept, though, that I know that art historians feel much the same way as computer visions do the term similar. It's not a bad concept, but it does tend to overdetermine relationships, including with materials whose relationships themselves overdetermined. So if you're looking for influence in the canon of, say, Western art, there's a lot to go around. And it does not necessarily descend in straight lines. It's divergent as well as convergent, and it's both conscious and unconscious. I don't think computer vision can deal with this deal with all of this by itself. What it always needs is ground truth where it exists. And this is an example of something that I would dearly love to do, which is a manual with computer vision, which is a manual aggregation of a visual cliche, the publishing industry's way of signaling that a book is about or something to do with Africa. So Simon Stevens, political scientist, manually assembled this set of book covers, which signify Africa or Africanness by an acacia tree at sunset. Sometimes you get an animal on board. And this kind of visual trope is sort of rolled out across diverse genres. Now, this is where I think kind of computer vision can very productively work with metadata, because yes, we can probably find these kind of similar features, but if we had access to something like Amazon's metadata, we could refine and trace this line of influence by genre, by publisher, by period, and do something that's kind of more fine-grained than either the kind of very specific feature extraction and instance-based recognition I started with, or the more broad image classification that I went on to discuss. And that's something that I think, interestingly, in relation to cultural heritage, brings together the kind of raw visual domain with exactly the forms of provenance identification and classification and reliable annotation that we need. Thank you very much. I'll await questions at the appropriate time.